Lesson 7-2, Converse of Pythagorean Theorem. So the converse of the Pythagorean theorem states that if a squared plus b squared equals c squared, then a triangle is a right triangle. Example, we're going to tell whether the given side lengths form a right triangle. So problem A, we have the sides 7, 24, and 25, and we want to know if they form a right triangle. So we are going to see if they fit the Pythagorean theorem. We need to identify which sides to plug in for A, B, and C. Always look for the longest side. In this case, that's 25. It's the longest side, and that means we're going to plug it in for C. So we have a squared, which a could be 7 or 24, so I'm going to use 7, and we'll square that. B squared, I'm going to use 24 for B, and we'll square that. And then c squared, we'll use the longest side, 25 for c, and square that. But I'm going to put a little question mark above the equal sign, because I don't know if they're equal or not. Next, we will just simplify. Continue simplifying after finding your squares. We're going to add. And I'll add, in the step above, we didn't know if they were equal or not, so we'll use a question mark. But now we see that 625 on the left is equal to 625 on the right, so that's true. And since this fits the Pythagorean theorem, it's a true statement, we can say yes, this is a right triangle. We're going to do another problem like this. B part, we have the sides 5, 12, and 8. We'll start by identifying the longest side, which in this case is 12. So that would be C. And then we'll plug in our values, and we'll see if this is true. So we will simplify. And then after simplifying, we get 89 is equal to 144. That is not a true statement, so I'm going to cross through the equal sign, so they are not equal. And since they're not equal, no, this is not a right triangle. Now we're going to talk about a proof about the Pythagorean theorem. This is going to go through the process of showing why this formula works. You have seen this diagram before today in practice or in activity in class, but we're going to just talk about it a little further today. We've got our formula, and now I'm going to include a diagram. Notice this diagram. I have 3 squares. In the middle of those 3 squares, you see a right triangle. These 3 squares represent a squared, b squared, and c squared, and the 3 sides of the right triangle represent a, b, and c. So if a were this side and b was this leg, that means the hypotenuse, of course, has to be c, the longest leg. I could measure those sides and see that a is represented by 3. So we'll plug that in, and we have a squared is 3 squared. And b is a length of 4. We're just counting the lengths of the sides of the squares. We plug that in here, and we have b squared. And then c is a length of 5 units. And so we can plug in 5 for c, and we have 5 squared. And so we can simplify, and we get 9 plus 16 equal 25. So notice over here where I have a, that if I were to say a times a, I would get a squared, which is 9. And you see that there's 9 units that represent a squared. Over here at this square that has the side b, if I were to say that side b times b, I would get b squared. And notice there are 16 little squares, or 16 units represented there, which is 4 times 4, which is 16. And notice that this square that has a side c, that if I found another side of it, it would also be c, because it's 5 by 5, and that c times c is c squared. And notice that c squared is 25 units, which is the same number of squares you get. Notice as well that if you add the 16 squares from b squared and the 9 squares from a squared, you get 25. And it happens to be that they are the exact same number of squares as c squared, 25. And that proves that Pythagorean theorem works. You could demonstrate this using 3 squares for any 3 sides that are true for the Pythagorean theorem. If it's a right triangle, this will always work.